Good afternoon. This is the short lecture on Friday, the 23rd of April, and it will have this format here. I will write on an electronic blackboard, and hopefully this will work. So today's topics are Gauss, and but first I will give a short introduction to Flux, and so it will be composed of two separate videos, and the first will be about Flux, and then there will be an introduction to Gauss. You will hear more about this next week at the long lecture on Wednesday. So the lecture is about flux. And what is the flux? The flux is the flow through a surface divided by time. So actually it's the flow rate. And let me give you a simple example. And it will be about sunshine through a 1D window with length 1. And first we look at, well, we think that this window is at the equator, so the sun rises at 6 o'clock in the morning. And we look at it at 6 o'clock. We have here this one-dimensional window, and we have the solar field, vector field, and it's perpendicular to the window. And it has the strength V. So this is the vector field. Now, if you look at the flow of this vector field, then in one time interval, it will advance like this, where this is the length of this distance here. So if you look at this rectangle here, then the flux is equal to the area of the rectangle, and this is this length of the solar vector field times 1, which is the length of the window, and this is simply the length of the solar field. Let's look at the situation at 12 o'clock. Then you have, again, you have this window here. But now the solar field is in this direction. And you see there's no flux through the window when the solar field is in this direction, or there's no flow through the window, so the flux is equal to 0. Finally, we look at, say, some arbitrary time. Again, we have the window. We have, say, we have the solar field is now in this direction. This is the vector field V. And so in one time instant, you have that the vector, the flow field has advanced like this. And again, the flux is the area of this parallelogram. And if you here have a normal vector to the flow field, then this distance here, or this, or the, you could say the height in the parallelogram is the dot product between n and the vector field v. That is a projection of the vector field onto the normal. So the flux is again the area of this parallelogram, and this will be equal to the normal vector times the v vector times the length of the window. So this will be n times v. Now let's look at a more general situation. We have in 3 space x, y, z. We have a surface, say like this. So this is surface, and you have a point P, and you have a normal vector to the surface, and you have a, say, a vector field V. Then the flux in P, in the point P, is equal to the projection of the vector field onto the normal vector. That is, it's this dot product. And then if this is the surface F, then the total flux is the integral over F of this dot product. I could indicate that this is a normal unit vector to the surface F. So this will be then the flux through Bn. Now let's look at the situation where you have a parametric representation of your surface. So if R of u comma v, where u is in the interval from A to B, and v is in the interval from C to D. If this is a parametric representation, then you can, so to speak, unfold this flux integral, making it into a double integral. So you integrate from C to D and from A to B, and then you take the restriction of your vector field to your parametric representation of the field, and then you take the dot product between this and the normal vector that is generated by the parametric representation. And this means that I could write here where n, I could again write an f because it belongs to the surface f. And this is the cross product between the derivative of the parametric representation with respect to u with the parametric or the derivative with respect to v of the parametric representation. So when we have this, and I will explain next on Wednesday why it is so, because somewhere here the Jacobian is hidden, and you will learn more about this on Wednesday. But for today, and for you to actually do the exercises after the lecture, then this will suffice. I will give an example here. And we're given a vector field and this is given by -3/2 times x, and then y squared plus z, 1. So these are the 3 coordinates of our vector field. And we are also given a surface f with the parametric representation. And let's see, we have that this is equal to u, v, u squared. And u belongs to the interval from 0 to 2, and v belongs to the interval from -1 to 1. So let's see if we can compute this flux here, which is written here at the top of the. So what we need first to compute the normal vector. Let's do that. We have the normal vector, and first you have to take the derivative of the parametric representation with respect to u. You get 1, 0, and 2u. That is 1, 0, and 2u. And then you have to cross that with the derivative with respect to v. The first coordinate doesn't depend on v, so that will be 0. The second is v, so that will be 1. And then finally 0. So if you compute this cross product, you get -2u, and then you get 0, and then you get 1. And then you need the restriction of your vector field to this parametric representation. So you have this vector field, which is at the upper part of the screen. And instead of x, you have to write you have to write u, so you get -3/2 of u, and then you get u squared plus v, and then you get finally you get a 1 in this vector field. So now you have the ingredients that you need in order to write down the flux. It will be the integral, I write it generally here, times unit vector f d nu. And when you unfold this with your parametric representation, you get this double integral where you integrate v from -1 to 1, and you integrate u from 0 to 2, and then you get -3/2 u squared plus v. This is the restriction of your vector field to the parametric representation, and then you dot this with the normal vector, and this is -2u 0 1, and then du dv. So you have to compute this integral, and you do the dot product, so you get that it will be -1 to 1 and 0 to 2, and then the integrand is u squared plus 1. Integrate with respect to u and with respect to v. So when you integrate, no, it will be 3u, and then you take this stuff, 3u squared plus 1. And when you take the antiderivative of 3u squared, you get u cubed plus u, and this should be taken between the limits 0 and 2, and then you integrate from -1 to 1. And if you put in the limits, you get 2 cubed, that is 8, plus 2, that is 10. And you can put that outside the integration sign, and then you get in -1. And this is simply the length of the interval, so that will be 2 equal to 20. So if this is the flux, then we have computed the flux as 20.